In this video, we are going to discuss about voltage controlled oscillator. So, uh, here the frequency of oscillation is determined by the RC time constants. So, this is a pin diagram of voltage controlled oscillator, that is NESC 566. Okay, and this is a block diagram of 566 VCO. So here you have it is a 8 pin dual in package, which consists of the first pin is ground, second pin is no connection, and the third pin is you have a square wave output and you have a triangular wave output, and the eighth pin is VCC, and seventh pin is C1, and sixth pin is R1. So you can see the sixth pin is connected to R1, and the seventh pin is connected to C1, right? And here you have a modulation input. Okay, so based on the value of the VC, the frequency will be changing. So it is used in the applications called frequency modulation, frequency shift keying, where the frequency need to be controlled by means of the input voltage, that is called as control voltage. Okay, so that is why it is called as a voltage to frequency converter. Okay, so this is also called as a voltage to frequency converter. So you can see you have two outputs, right? One is square wave and another one is triangular wave, right? So let me consider that I'm going to produce a square wave like this. Okay, this is my square wave, and this is called as VSAT, and this one is minus VSAT value. Okay, this is minus VSAT value, and the VSAT value is nothing but VCC, and the minus VSAT value is 0.5 VCC. Okay, let me take like this. You know that here I have connected a skimmer trigger, right? So you know the block diagram of skimmer trigger, right? So this is how the skimmer trigger will look like, right? So it has a positive feedback, right? And you can see RA and RB is connected like this. So VA is my input pin. Okay, so we know that in order to find the VB value, so VB is nothing but V saturation, right? V saturation into RB divided by RA plus RB, right? So suppose if V naught is V saturation, so VB is equal to V saturation into RB divided by RA plus RB. Okay, so if RA and RB is equal, I can write this is equal to V saturation divided by 2, right? This is my VB. So here VB is nothing but V upper threshold frequency, right? So since it is a skimmer trigger, okay, and what is VLT? So if it is minus V saturation, I can write VB is equal to minus V sat into RB divided by RB plus RA. So if RA is equal to RB, I can write VB is equal to minus V sat divided by 2, right? So this is nothing but my lower threshold voltage, right? So what is VCC? VSAT? VSAT is nothing but VCC, right? VCC by 2. And what is minus VSAT? Minus VSAT is nothing but 0.5 of VCC, right? Divided by 2. So I can write my VULT. Sorry, VT is equal to 0.5 of VCC, and VLT is equal to 0.25 of VCC. Okay. So consider if you see in the diagram, okay. So here the input is from the capacitance, right? So if the capacitance voltage increases beyond the VUT value, so the negative values. So what I'm telling is, so here if you see, here I have a capacitor. So if the capacitor is charging more than VLT value, VUT value, so negative is greater than VI, V minus is greater than V plus, you will get the output as that is V naught as equal to V saturation. Okay. So suppose if V minus is sorry, minus V saturation, V plus is greater than V minus, means V naught is equal to V saturation. Okay. So if suppose if my capacitance is charging, okay, so it's charging, let me take it is charging from so this is how it is charging. Okay, this is my VC. Okay, the voltage at VC, and I have a threshold voltage, right? Two threshold voltage, right? One is VUT and another one is VLT. So VUT is nothing but 0.5 VCC and VLT is 0.25 VCC. So if that is the case, I'll get the, so here you can see the VC value is greater than VLT value, VULT value. So my output goes to 0. Okay. So again, if you see, if the VC values goes below this VLT value, my output goes to this is VCC, right? The ECC. So again, at this point, so this is how I will get the square wave, right? So let me take. So if you see the diagram, so here the fifth pin and sixth pin is connected to a capacitor. Okay, through the capacitor. So let me consider this uh, the capacitor C1, okay, is initially charged or discharged by this constant current source or sink. So the amount of current can be controlled by changing the voltage VC that is applied at the input pin, or by changing the timing resistors R1, which is external to the chip. Okay. So the voltage at the pin 6 and 7 are held at the same voltage. So if this is VC, this is also VC. So the current flowing through this resistor R1, I can write current flowing through the resistor R1 is I. I is equal to V plus, here V plus minus VC divided by R1. Okay, so V plus here it is nothing but VCC. Okay, so this is a modulating input and R1. Okay, so I know that I is equal to dq by dt. So this I can write it as C1. Okay, C1 is a capacitor that is responsible for the charging and discharging, dV divided by dt. Okay, so what is del V? So if the capacitance is charging, it is from so you can see the change in the voltage, that is nothing but 0.25, right? So the change in the capacitor voltage is nothing but this del V. So C1 into 0.25 of VCC, right? This is a change, and this is nothing but if this is a time period, right? So can write this is T. Okay, so this is T. I can write this is nothing but del T. Okay, if this is del T, this is also del T. Okay, so I can write T is equal to 2 del T. Okay, so del T. Okay, dt I can write it as del T. Okay, so I can substitute this is my first equation and this is my second equation. So you substitute first and the second equation, I will get VCC minus VC divided by R1 is equal to C1 of 0.25 VCC into del T. Okay, so now I can write del T. Del T is equal to C1 0.25 VCC R1 divided by VCC minus VC. So you know that 2 del T. What is 2 del T? 2 del T is equal to 0.5 VCC R1 C1 divided by VCC minus VC. Okay. 2 del T is something but T. So T is something but 1 by F. So I can write F is equal to VCC minus VC divided by VCC R1 C1 into 0.5 I can write as 2. Okay. So if so the here I can write this VC value. Okay, the VC value is changing from VCC to 3 by 4 of VCC. Okay. So from this arrangement, I can tell the free running frequency is depends on the value of VC, R1 and C1. Okay. So here this R1. Okay. So the R1 it is ranging from 2 kilo ohm to 20 kilo ohm. Okay. And VCC is nothing but plus or minus 5 ohm. Okay. Or it may be to 12 volt. Okay. Plus and minus 12 volt. So this VCO is commonly used in converting a low frequency signal such as EEG, EKG into audio frequency ranges. Okay. So suppose if we see in this one, I'm going to substitute this VC. So the VC is equal to 7 by 8 of VCC. So if that is the case, what will happen? So this is my third equation and this is my fourth equation. So you substitute 4 in 3. So if I substitute VC is equal to 7 by 8. Okay. 2 into VCC minus 7 by 8 of VCC. VCC R1 C1. Okay. So I'll get 2 divided by 8 VCC divided by VCC R1 C1. So I'll get 0.25 R1 C1. So this is nothing but my F naught. Okay. That is free running frequency. So let me write voltage to frequency conversion factor. So that is nothing but kV. Okay, that is equal to, what is my output? Output is nothing but frequency, right? Del F naught divided by del VC. Okay, so this del VC is nothing but modulation voltage required to produce the frequency shift del V naught, del F naught for a VC. Okay, so let me assume my original frequency is nothing but so this del F naught represent F1 minus F naught. Okay, so this is my original frequency. How far it is differ from the my uh, new frequency. So this is nothing but del F naught. So this I can write it as 2 into VCC minus VC plus del V, right? Del VC divide by, so this is a change, right? Um, divide by VCC R1 C1, right? VCC R1 C1, VCC R1 C1 minus 2 into VCC minus VC divide by VCC R1 C1. So this I can write it as 2 VCC plus del V, del VC divide by, sorry, 2 del VCC del VC VCC R1 C1, right? So my del VC is nothing but del F naught into VCC R1 C1 divided by 2. So you know what is F naught, right? F naught is nothing but 0.25. So from the equation 6, right? From the equation 6, I can write what is R1 C1? R1 C1 is equal to 0.25 of F naught. Okay, so you substitute this sixth equation, in this formula. So I will get del F naught VCC. What is R1 C1? It is nothing but 0.25, right? 0.25 2 into F naught. So this is nothing but del F naught VCC divided by 8 F naught. Okay, so from this I can write what is kV, right? kV is equal to del F naught divided by del VC. That is equal to 8 F naught divided by VCC. Okay, so this is how if you see if the modulating voltage at the pin 5 is increased, the voltage at the pin 6 is also increases because both are connected short circuited, right? So which will result in the less voltage across the R1, thereby reducing the charging current. Okay, so the voltage across the capacitor C1 is applied to the inverting input of the inverting terminal of the schema trigger via buffer amplifiers, right? So if you see here, I have applied this to the schema trigger. I have applied this C1 capacitor to the inverting uh, terminal of the schema trigger, right? And output voltage of swing of the schematic is designed to VCC to 0.5 VCC. So if RA is equal to RB, we know that the VUT and VLT values 0.5 VCC and 0.2 VCC. So when the capacitor, when the voltage on the capacitor C1 exceeds the 0.5 VCC, the output goes low, and if the capacitor discharge and when it is 0.25 VCC, the output of the schematic goes high, right? So since the source and the sink current are equal, the capacitors charges and discharges for the same amount of time. So this will give a triangular voltage waveform across the C1, right? So which is also available at the pin 4. The square wave output of the schematic is inverted by the buffer amplifier at the pin 3. Okay. So you have the output waveform which is shown in the near the pin 4 and 3. So we know that the F naught is equal to 2 into VCC minus VC divided by R1 C1 VCC, right? So the output frequency of the VCO can be changed either by R1 C1 or by the modulating input terminal, that is modulating input voltage VC. Okay. So the voltage VC can be varied by connecting a resistor R1 and R2, which is shown in the figure, right? So here you can see R2 and R3. Sorry, this is not R1 and R2. This is R2 and R3. So here you can see the VC is nothing but VC is equal to V plus into R3 divided by R3 plus R2. So if with the help of this R3 and R2 value, I can change the value of VC. Okay. So there's a mistake. Okay. R2 and R3. The compound R1 and C1 are first selected so that the output, the VCO output frequency lies in the center of the operating frequency range. Now the modulating input voltage is varied from 0.75 VCC to VCC. So which can produce a frequency variation up to 10 to 1. Okay. So let us discuss on problem based on this. So the CA is a capacitance whose value is 0.001 microfarad, which is used to eliminate the possible oscillation produced in the current source or current sink. Usually the frequency which is ranging from 500 kilohertz to 1 megahertz. Okay. So this is my VC, and they are asked to find the output frequency. So the F is equal to 2 VCC minus VC divided by VCC into R1 C1, and C1 value is 0.001 microfarad, and VC is 12 volt, VCC is 12 volt, and VC is nothing but 12 volt into R3, that is 15K divided by 15K plus 2.2K, right? So if I solve, I will get the answer as 10.45 volt, right? So I substitute in this formula. F is equal to 2 into 12 minus 10.45 divided by 12 into R1 is nothing but 15K, and C1 is 0.001 microfarad. Okay. So if we solve, you will get F is equal to, that is my output frequency, is equal to 17.06 kilohertz. Okay. Next, change in the output frequency if VC varies from 7 to 8 volt. So F is equal to 2 into 12 minus 7, right? Divide by 12 into 5, routine K into 0.001 microfarad. So if you solve, you will get the answer as 55.56 kilo. Okay. So if F2 is equal to 2 into 12 minus 8, here VC is 8. So divide by this denominator value, you will get to 44.44 kilohertz. So change in output frequency is f1 minus f2, that is answer is 11.112 kilohertz.